Do you know how Uber predicts the estimated time of arrival, or ETA, for the trips? In this video, let us understand the machine learning system that drives the ETA prediction at Uber. Firstly, let us understand classical routing engines that predict ETA without using machine learning. Routing engine first transforms the road network into a directed graph. The weights of the edges of this directed graph represent the estimated time to travel that particular edge. To calculate ETA, we can use the shortest path algorithm and find the minimum weighted path. But there is a problem with this type of routing engine. It fails to capture information like terrain details, road and traffic conditions, etc. Due to this, the calculated ETA is often not very accurate. To solve this, we can build a machine learning model that incorporates real-time features like traffic conditions, recent car crashes, etc. To do that, we first take the base ETA calculated by the routing engine. Then we build an ML model that takes this base ETA and other real-time features as input and predicts the residual change. This residual change is nothing but the predicted adjustment value in the base ETA based on the real-time features. To avoid predicting negative values for ETA, we take its max with 0. Finally, this predicted ETA is sent to the user. Let us dive deeper into the machine learning model that predicts residual change. The ML model can be divided into two high-level components: sparse parameters and dense parameters. The parameters associated with features of the model are sparse parameters, and the parameters of deep neural network layers are dense parameters. Sparse parameters are the embeddings created by the input features. But how do we create such embeddings? The discrete features like type of user or type of trip are usually categorical features. It means that the values of these features will be one of the few predefined categories. We can initialize an embedding lookup table for each feature. The rows of this table represent each category of the feature, and it contains the vector of a certain dimension. This vector is called embedding of that category. When we want to find the embedding for the particular feature, we will look up the embedding table with the value of this feature and extract the embedding. This embedding can now be used as input to the dense parameters of the model. But wait, this method is only valid for discrete features. What about continuous features like the user's age or number of past orders? These features can contain continuous numeric values. To create embedding for such continuous features, we can manually create categories with specific ranges of the values. This process of transforming continuous features into discrete features is also called discretization or bucketization. Now we can follow the similar process as we did for discrete features. We can create an embedding table for each feature and look up the value of the feature in this table to extract embedding. Once we extract embeddings corresponding to features, we can feed these embeddings into the dense part of the model. By the way, if you are watching till now and if you think our videos are worth watching, then please consider being a member of this channel by clicking on the join button. Creating such high-quality videos takes a lot of effort, and your contribution will help us. In return, you will get to attend our monthly Zoom meetups where we discuss about ML, system design, and career growth strategies. Coming back to the topic, what is this dense part of the model? The dense part consists of encoder and decoder. The encoder is responsible for performing feature interaction, whereas the decoder takes in the composite feature created by the encoder and predicts the residual change. Uber's ML system uses a transformer encoder for feature interaction, and it contains two different layers for decoder. The first layer in the decoder is a standard fully connected layer, whereas the second layer is a bias adjustment layer. But what is this bias adjustment layer? Note that this same ML model will be used for all the scenarios where we might need to predict ETA. For example, this model will be used for predicting ETA for short trips as well as long trips. It will be used for pickup trips as well as drop-off trips. It will be used for ride trips as well as food delivery trips. Depending on the scenario, the underlying data distribution would change, and thus, the model's output distribution should also change. To enable this, we create a fully connected layer called bias adjustment layer. This layer takes two inputs, the fully connected layer's output and features corresponding to types of scenarios. To train this model, we calculate the loss function using the predicted residual change and the actual residual change. Uber uses Huber loss as a loss function. Once the model is trained, We create a copy of this model for serving. Whenever the user schedules a trip, the Uber services will internally call the ETA service. The ETA service first calls the routing engine to get the base ETA. It also extracts other user features from the data store. Then it calls the serving ML model to get the predicted ETA. This predicted ETA is shown to the user. When the trip is complete, the predicted ETA and actual ETA is stored in a separate data store along with features used for prediction. Later, the training version of the model is regularly fine-tuned with this newly accumulated data. Once fine-tuned, the model parameters will be synchronized with the serving copy of the model. This type of model fine-tuning is usually performed after certain interval of time, maybe certain hours or certain days, depending on the volume of the accumulated data. So this is how Uber predicts the expected time of arrival for its business. I hope you have found this video useful. Please like the video, share the video, and subscribe to the channel. Comment down any questions and the feedback that you might have. See you in the next one.